The total inlet gas flow to the tower is 30 kilomoles per hour. Let's understand that. Total inlet gas. So it includes the inert value and the acetone. It includes both the inert and the acetone and the solute. And that flow rate is 30. The total inlet pure water flow. Pure water flow. That is telling us that the water that's coming in doesn't have any solute, doesn't have any acetone. Okay, so the pure water that's coming in is used to absorb the acetone, and that is flowing at 90 kilomoles per hour. 90 kilomoles per hour. The process is to operate isothermally at 300 Kelvin. Total pressure is 101.3 kPa. Equilibrium relation between acetone and in the gas and the liquid is given. So I don't need to go and check in the tables what Henry's constant is, etc., because the equilibrium value is already given to me, which means that H prime is 2.53. So it's given to me. And you are asked to determine the number of theoretical stages required for the separation. Okay, how do we do this? If I want to determine number of stages, I need at the end to plot a graph of y versus x. I need the equilibrium line. I need the operating line. And I must be able to step off between the operating line and the equilibrium line in order to get to the number of stages. Where do we start? So I don't draw a graph that's 0 to 1, 0 to 1 there, because I may be operating only in a small part of this graph. So therefore, when you're plotting your graph, you need to work out what the maximum values are. And when I work out what the maximum values are, then I can expand my graph so that it fits the graph paper that I'm using, and I'll be able to construct my diagrams properly. Okay. So let's go through the question again. Desired to absorb 90%. 90%. The gas coming in originally has 1 mole percent. 90% of that must be absorbed. Total gas flow rate into the tower, 30. And the water flow rate is 90. You are given temperature and you are given pressure. Okay. How do I work out the maximum and minimum values in order for me to plot this graph? I got to work out what. Let's put it into the tower here. In the tower here, you've got L0, X0 coming in there. Coming out here will be X1. Well, let's call it Xn. Okay, Xn, because it's n number of stages, not one stage, n number of stages. Going up here will be Yn plus 1. Okay, and coming out on the top will be Y1. So my x-axis on my graph must be able to accommodate the values from x0 to xn. Okay, it must be able to accommodate that. So I must be able to plot xn here somewhere. Let's take the 1 out. I must be able to plot xn somewhere. Okay, and x0 coming in, you know that it's pure water, so that is 0. So I have to start at 0. So on my x-axis, I must be able to plot all values between 0 and xn. Okay, so I need xn. I need to find out what xn is. On the y-axis, I've got yn plus 1 and y1. I must be able to plot this in the graph as well. Which would be the higher value, y1 or yn plus 1? Which would be the higher value?
Yn plus 1, sir.
Yn plus 1 will be higher because that is what's coming in. I am going to absorb some of the acetone from it. So the y1 that's going out will have a lower value. Okay, so therefore let's take out the 1 there, it can't be 1. Yn plus 1 will be somewhere on the top, and y1 will be somewhere at the bottom. Okay, now I need all these values. I have to have all these values in order for me to know how to do the stepping off on the graph. So what I want you to do now is take a few minutes to do the material balance and tell me what the values are for x0. Well, x0 we know, x0 is 0. Okay. Tell me what yn plus 1 is, what xn is, what v1 is. Once you have that, then we'll be able to put it into the graph. So I'm going to give you a few minutes. You're going to work through that, and then we'll come back and discuss further. Are there any questions before you attempt this? No questions. Okay, I'm still around. I'm not leaving. So if there's any questions, any problems that you're experiencing, let me know, and we can address them. Okay, I'll give you a few minutes just to work out those values. Go for it.
Sir.
Yes, go for it.
Can you please go to the previous slide so we can verify the formula?
This one?
No, the slide.
This one?
Yes, this one.
Right.
Yes.
But then now you don't have the values. Okay, you can write this equation and then I'll explain it just now. Okay, you got the equation? I can go back to the question.
Yes, sir.
Now, once I draw this diagram, I should be able to write that equation because it's a mass balance equation. So what's coming in is equal to what's going out. Okay. So once I have the diagram, you should be able to, from this diagram, do your mass balance and material balance. It's important to do that because sometimes the symbols I may use are different. So from your diagram, you should actually write the material balance equations. Anyway, go for it. Okay, are we getting there? You got one or two of the values already? Okay, I hope you're getting somewhere. Let's go through this. So you've got x naught already. We know that x naught is 0. Okay. Xn we need to evaluate. We need to evaluate yn plus 1 and y1. Let's look at yn plus 1. From the problem given to us, what would be yn plus 1? Yep.
It's gonna be 0.01, sir.
Okay, so it's 1 mole percent, so therefore it is 0.01. All right. Now I need to evaluate xn and y1. How do I do this? Let's try to analyze the problem and let's see whether we can get to that. So the amount of acetone entering here through we want to work out V1 and V prime, the amount of acetone entering. That will be equal to 0.01 of 30. Right, because 30 is the flow rate. 30 is the flow rate and 0.01 is the concentration. That gives us 0.3. So 0.3 kilomoles per hour coming in. That is the acetone coming in. What would be the air that is coming in? So what would be V prime? V prime must be equal to the inert, the air that's entering. What will be the inert?
It's 90, sir. 90 kilomoles per hour.
It's not 90. Remember, why would you say 90?
Yes, air is pure, sir. In this case, we are told that pure air. Yes, air is pure in this case.
Right, but where do you get 90 from?
From the equation where y prime is equal to v times 1 minus y a 0. Yes.
So you're saying from here, v prime equal to v into 1 minus y. Are you using that?
Yes. Yes.
And what is v?
V is equal to 30. V is equal to 30. But in this case, I think we are interested with what? With L or what?
Yeah, I think you're confusing the L and the V's. Okay, so let's look at it this way. Let me erase this. Let's go back, right? I know that the total flow rate of both acetone and air coming in is 30. Total inlet flow rate is 30. That's what I'm told. So the air that's coming in, that's the total flow rate. The air that's coming in can't be greater than 30 because the total flow rate is 30. The amount of acetone that's coming in with that system is 0.3. We just calculated. So the air that will be coming in will be 30 minus 0.3. Which is 29.7. Are you with me, people? Hello? You with me?
Yes, sir.
All right, cool. So that's V prime. If I've got V prime, now I'll be able to use that information in order to calculate Y1 on the top. I got Yn plus 1. I can calculate Y1 because what's coming in here is 29.7A. Going out on the top will also be 29.7A. Okay. Let's look at the acetone that is leaving. Acetone, amount of acetone leaving will be equal to, how do I work this out? If I've got 90% of the acetone must be absorbed, so coming in is 0.3, 90% of this must be absorbed, then how much is leaving? It will just be the 10%, isn't it? So 0.1 of whatever is coming in, which is 0.3. 0.03. Okay, so that's what's leaving. Maybe we should say leaving in V1. Okay, so that's in the gas stream. So the amount of acetone leaving in Ln will be the 90%. So 0.9 of 0.3 equal to 0.27. You still with me, people? Anyone confused? The silence tells me that no one is confused. So if there's any problems, you need to address it, please, so that you'll be able to follow as we move along. All right, 0.27. What would be V1? If I can work out V1 and Ln, the total flow rates, then I'll be able to work out the concentrations from there. Okay, so what would be V1? V1 will be equal to, it will be the total amount of acetone that is leaving with V1. And where do I get that? 0.03 plus the air that is leaving, the inert air that is leaving. And we worked that out already. So the total V1 will be equal to 29.7 plus 0.03, which works out to be 29.73. Which means, if that is the case, which means that V1, Y1 will be equal to the amount of acetone that's there over the total amount. We're working mole fractions now. Mole fraction. So it is the moles of acetone divided by the total moles. Total moles is given. Here's 29.73. That's the total moles. How much of this is acetone? How much of this is acetone? 0.03. So it'll be 0.03 divided by 29.73, and you get an answer of 0.00101. People, you okay? You with me? Do I need to repeat that?
Yes, please.
Sorry, you saying repeat or you saying you okay?
Repeat, sir.
Repeat. Okay, let's go through that again. How do I work out mole fraction? What is mole fraction? Mole fraction is the moles of the particular component divided by total number of moles. That's mole fraction. And that's what I want to find out. This V1 that I've got here is mole fraction. So if I know the amount of acetone coming out and I know the total moles, then the amount of acetone divided by the total moles will give me mole fraction. Okay. How much of acetone is coming out? We already worked that out. Amount of acetone leaving in V1 is 0.03 kilomoles per hour. So that's what I worked out. What is the total number of moles coming out? Total number of moles must be acetone, which is 0.03, plus the inert air that's coming out. Inert air that's coming out, 29.7. So if I add the two, I get 29.73. Working on mole fraction, amount of acetone, which is 0.03, divided by the total number of moles, will give me the mole fraction Y1. You with me now?
Yes, I'm following, sir.
Cool, cool, cool. We do the same thing for the other side. So I want to work out Xn and Ln. Okay, how do I work out Ln? Ln will be equal to, this is the total flow rate coming out. So it will be equal to the total water that's coming out, which is the L prime, plus the amount of acetone that's coming out. Okay, plus the amount of acetone that's coming out. So what is the water that's coming out? It's the same as the water that's going in. So 90 kilomoles per hour was L prime. Okay, because it had no acetone coming in. So it had pure water, 90 kilomoles per hour. That was what was entering. That will be what is leaving at the bottom of the tower. But I have to add to that the amount of acetone that is leaving. Amount of acetone leaving in Ln is 0.27. So if I add the two, I get 90.27. How do I work out the mole fraction for Xn? Xn will be the amount of acetone divided by the total number of moles. How much of acetone we've got is 0.27 divided by 90.27, and I get 0.03. Sorry, 0.003. Questions, people? Anyone confused? Anyone unsure as to how we got these values? All right. Those that are struggling, you may want to look at the video again and listen to the explanation again. And if you're still having a problem, obviously contact me and we'll try and solve it. So now that we've got that, we know that yn plus 1, which is on the top here, is the maximum value. So this maximum value is 0.01. Now you can see what a small value that is. So if I plotted my graph from 0 to 1, then once I get to 0.01, that is where my entire graph is going to be, my entire construction. So I can't plot a graph like that. I've got to work out these values before I start plotting. Okay, so the maximum 0.01. What is the minimum? What is y1? Y1 we worked out to be 0.00101. Very, very small value. And you have to plot it on graph paper. On the x side, you must start at 0 because x0 is 0. So it must start at 0. And it goes to xn. What is xn? We just worked out to be 0.003. That's xn. All right. Once I plot this, and I've got the equilibrium line and the operating line. Okay. So if the equilibrium line is easy to plot because the equation is given to me. That's easy to plot. The operating line, we're assuming it is a straight line. If it's not a straight line, you have to use the operating line equation in order to plot it. Okay, but if we assume it's a straight line, and it will be a straight line if we're using very small values, as you can see here, very, very small values. So dilute streams, then this operating line will be a straight line. If it is a straight line, then I only need 2 points to plot this graph, to plot this line. And what are those 2 points? It is at the top of the tower and at the bottom of the tower. So let's look at the top of the tower. At the top of the tower, x0 is 0 and y1 is 0.00101. So there's the point here. That's 1 point on the operating line. The other point on the operating line is at the bottom of the tower. I've got yn plus 1 and I've got xn. So yn plus 1 is here, xn is there, and that gives me the second point. And then I can draw this operating line. Not freehand sketches like what I'm doing. It's got to be drawn on graph paper with a ruler. Make sure they are straight lines, etc. All right, I want to work out number of stages. How do I work out the number of stages? I am starting off at 0.01 at yn plus 1. I'm starting off, that is what's coming in. I'm starting from here. I want to end up here. Okay, so I start stepping off. And so on. Obviously, my construction is incorrect. You should get, if you draw on graph paper, you should get 5.2 theoretical stages. Okay, you should get 5.2 theoretical stages. So you need to attempt this. You need to draw it on your own, put it on graph paper, do the constructions, make sure everything is correct. And that is what the solution looks like. Let's look at this again. There's y1 xa naught. There's the point there. There's yn plus 1 and xn. Okay, so those are the 2 points. You got the equilibrium line, you've got the operating line. The graph starts off at the bottom because we count our stages from the bottom going up. Okay, so even if you did it from top coming down, you'll get the same number of stages. But here, stage 1 is from the bottom of the tower, so therefore we got it from the bottom, which is 1, 2, 3, 4, 5. That's 5 stages. Okay. 6th stage would be here, which is going beyond what I require. So therefore, it's working out, and you have to physically measure and work out the fraction. And that is how we get an answer of 5.2 theoretical stages. In other words, when it says theoretical, we are assuming that all these stages are equilibrium stages. So it is 5.2 equilibrium stages, and therefore you can get a fraction. But for real stages, then you have to work out the efficiency of each stage. So if, for example, the efficiency of each stage is only 50%, then instead of 5.2 stages, I actually need 5.2 divided by 0.5, which will be 10.4 real stages, But in real stages, if I'm using plates in order to construct this real stage, for real stages, we'll talk about the equipment under distillation. Okay, we'll talk about the tower and the plates, etc. under distillation. So if I'm using plates in a tower, in order to give me the different number of stages, then I can't get a fraction for real stages. Okay, that's not possible, because I'm not going to get half a tray. So when I work out real stages, the number of real stages, if it works out to be a fraction, I must go up to the next whole number. So it will actually be 11 stages that's required, or 11 plates that's required. I can't come below that. I can't come to 10. Because if I work with 10, then I'll be below my required exit concentrations. I've got to go to the next level, the higher level. And therefore it works out to be 11 stages. People, any questions here? Okay, no questions. I've gone through these 2 problems extremely slowly. I went through it step by step and very slowly. We're not going to do all the examples like this. We have to move a little bit faster than what I've done now. But I needed to go through this slowly because I wanted you to understand the basic concepts. The next couple of problems that we do, we'll be moving much faster. I don't know whether you've got graph paper with you already. You should, since I told you on Tuesday to get graph paper. But if you don't, just make sure that by the next lecture you have it with you, because you're going to do the construction in class. Okay, you must be able to follow the example in class. So you must be able to do the constructions in class as well. And then you'll know if you get experiencing any problems, you'll be able to ask me, to repeat certain sections, etc.